Okay, without further ado, let's welcome our last speaker of today, Qiaochu Ma from Texas A&M University. His talk is bounding topological invariants using scalar curvature and isoperimetric constant. So, okay, Qiaochu can start whenever you're ready.
Okay, thank you. Thanks for the kind invitation. So my talk is about bounding topological invariants using scalar curvature and isoperimetric constant. So I shall start from very beginning. Suppose that now we have a Riemannian manifold M with a Riemannian metric GTM. And suppose that the dimension of this manifold is M. And well, with this Riemannian metric, we can construct the Levi-Civita connection and the Riemannian curvature. This is L, Levi-Civita connection. And the curvature tensor y, zw, where all x, y, z, w are vectors. Okay, so using this curvature tensor, well, we can construct first something called sectional curvature. Denoted by sectional curvature. So for any, now we have two vectors. The sectional curvature is given by -1. And actually, sectional curvature contains almost all the curvature information. So you can do some, using some tensor calculation, you can, from sectional curvature, you can go back to curvature tensor. So these two tensors, they are somehow equivalent. So no much information lost. And next step, we can construct the Ricci curvature. Ricci curvature is just the trace of curvature tensor. You have two vectors x and y. The Ricci curvature is given by the trace by EI, where we take the summation for this EI. EI is an orthonormal basis of the tangent bundle. Okay, so taking the trace for curvature tensor, so of course you lose a little bit information. The next step, we can take a trace again to get scalar curvature. It is just as its name, it's a scalar, so there's no actually not a tensor. So it is the trace of Ricci curvature. Summation is also for an orthonormal basis, and we can expand it. Okay, so from curvature tensor to scalar curvature, we take trace twice. So this step we lose even more information. So to some extent, scalar curvature is the weakest curvature invariant, and it has very different behavior compared to sectional curvature and ridge curvature. So for sectional and ridge, they are very rigid. But for scalar curvature, it's very flexible, and we can compare them. So take some examples. This classical result by Gromov, for example, for if a manifold has no negative sectional curvature, then we have an upper bound for its Betti number. This sum Bi is the sum of Betti numbers. This has an upper bound. This constant Cm is a universal constant, depend only on the dimension. This is dimension. So we can see that if you pose some bound on scalar curvature, so you have a very strong constraint on the global topology of this manifold. The manifold cannot be very you can say complicated because the Betti number has a universal upper bound. Or let's see an example from ridge curvature, also a classical result by Shaoyuan. If the ridge curvature has a lower bound and the manifold has a diameter less or equal to pi, then this manifold M is isometric to the standard M-dimensional sphere. Okay, so this is also very strong. We have lower bound on ridge curvature and some geometric information, then we can say that M is isometric. It's a very strong geometric property. So from these two examples, we can say that sectional curvature and ridge curvature are very rigid, and compared to them, scalar curvature.
You probably mean the diameter is exactly equal to pi?
Okay, sorry, it's exactly equal to pi. Yes, you're right. Thank you. Well, and for scalar curvature is very flexible. Let's recall theorem by Kajda and Warner. The theorem asserts that for a manifold with dimension more or equal to 3, and we choose any smooth function fx on this manifold, and suppose that there exists a point, any point, such that f, the function, is negative at this point, then there exists a metric or a Riemannian metric such that the scalar curvature is just this function. Okay, so seems that you can see almost all the functions can be realized as the scalar curvature of a matrix. It seems that there is no constraint at all, but actually this flexibility, it has a limit. Okay, the situation is where if okay, so this theorem for a case not covered by this theorem, what if fx is strictly greater than 0 for any x? And what happened? Yeah, we do have some topological constraint. This is the Lich-Norovich formula. Lich-Norovich theorem asserts that if M is spin and is it has a metric with positive scale curvature. Okay, this is condition 1, condition 2 together implies that a hat genus of this manifold is 0. Let me explain a little bit 1, 2, 3. So 1 and 2 implies 3. So first, spin. Spin is pure topological condition. There's no geometry at all. Uh, Actually, we only need its Diffie-Hellman class. It's a characteristic class in Z2 cohomology of degree 2. When it is 0, this manifold has a spin structure, and a hat. This a hat is a characteristic number 3 plus 3. A hat m is integration over m or a differential form. This differential form is a little bit complicated. It is okay. It takes this form where RTM is the curvature. Okay. I want to put the remark here. This determinant is actually, let's denote this by a hat RTM, the a hat class. This a hat class is actually the sum. This differential, it has many components. It has 0 degree. Its 0 degree is just 1, and a 4 degree 4. That's by 4, and 8. And so on. So this integration, we only use the top part, where top is just the order is the dimension of this manifold. Okay. And this part, this remark, we shall use it later, this lower degree part. All right, so we can see from this theorem that the positive scalar curvature, this flexibility, has a limit because we can consider, on the contrary, M spin with positive scalar curvature. So the A has genus, this characteristic number is 0. On the contrary, if M is spin and A has genus of this manifold is not 0, then so there is no positive scalar curvature metric on this manifold. And we actually have plenty of examples with these two properties, both spin and A hat genus non-vanish. So we have family of of manifold, yes, positive scalar curvature is not that flexible. And this is the starting point of our this project. So we have, let's consider some question. Question one. So question one. Positive scalar curvature seems too strong. So what if we have, let's consider the infimum of the scalar curvature denoted by K0. And okay, what if this K0 is less than 0? Okay, so it's not positive scalar curvature, but can we still control this A hat genus? First question. And the second question, question two. Okay, let's go back to this A hat genus. It has many components, degree 4, degree 8, and degree top. So this A hat genus, we only use its top degree part. So the question is, how about the lower degree? This, for example, 4. It had 8. There's no non-top component of A hat genus. So can we control them? Okay. Let's begin with the first one. First question. Okay, so first we review the review the proof of this Lichtenroich theorem. It follows from the combination of two theorems. The first one is Atiyah-Singer index theorem. If, okay, now M is spin manifold, then we can construct a spinor bundle over it. Spinor. Let's denote by SM over this manifold M, this vector bundle, and it decomposes as two parts, the positive part and negative part. It has parity. Okay? And using this data, we can also construct a Dirac operator acting on the sections of the spinor bundle. And also, this operator, Dirac operator, it changes parity. So if actually we can write it into a matrix form. So it maps the positive part. This is SM positive, SM negative. So it maps positive part to negative part and the negative part to the positive part. Okay. The Atiyah-Singer theorem asserts that this A hat genus, this characteristic number, is given by the difference of kernels of these two parts. Okay, so and this is the Atiyah-Singer index theorem, and the next one is Lichtenroich polynomial. I think Qiaochu might not be the earliest one who found this formula. Also, due to Schrödinger and other mathematicians, Qiaochu formula says that the square of the Dirac operator is given by two parts. The first part is this is the positive, the non-negative Laplacian. So yes, so you should put a -1 in front of the usual one used in analysis. +1/4 the scalar curvature. Okay, so using this theorem, you can see that if the scalar curvature is positive, then okay, dm dsm square, it is a non-negative one plus a non-negative one. So the kernel of this operator can only be zero, just zero. Therefore, okay, both this part and the kernel of the positive part and negative part are zero, zero. So A hat genus is zero by the single index zero. A hat genus is zero. Okay, and for, we shall follow the proof of this Lichtenau-Rowisch formula to get our first result. First result is suppose that again M is spin, and the scale curvature greater or equal to K0 lower bound, which is less than 0. And then there is a constant, universal constant, only depend on the dimension M. Such that the A hat genus, its absolute value, can be controlled by the first is the lower bound of the scale curvature with the power and the volume of the manifold over in this is isoperimetric constant of this manifold. So remark one, let me explain this isoperimetric constant. It is the infimum. Okay, suppose that the manifold takes the form of this. This is the whole manifold, and we shall take a hypersurface like here, S, and divide the manifold into two parts, omega 1, omega 2. So we shall take infimum for all S and compute the area of S over minimum of volume omega 1 and volume omega 2. With the power. So with this normalized power, this isoperimetric constant is independent on the so if we make this change, so multiply by a constant t, this isoperimetric constant is not changed. Okay, so it is on the denominator. So if you want it not too small, so this is not too small, it means that you don't have this manifold doesn't have a very long nick. So we abandon this, throw away. And okay, actually this, I want to put the second remark. This isoperimetric constant, you cannot remove it. Okay, not, you cannot throw away. So actually, the following inequality is incorrect. This is incorrect. Indeed, we can find a sequence of, let's put a parameter k. We can find a sequence of manifold with the same dimension such that they have genus over k0 of h and k. This goes to infinity. So we can, so let's compare with this original inequality. So we cannot just remove this isoperimetric constant. So, this inequality is to some extent optimal. Okay, so let me briefly describe the proof of this result. So by the Atiyah-Singer, we call the Atiyah-Singer, A hat Atiyah-Singer. A hat is the difference of kernel d plus minus kernel of d minus part. So we want to control the absolute value of A hat genus. So equivalently, if we can control the dimension of the kernel of Dirac operator, okay, put them together, not the difference, but the sum, then we can control the A hat genus. Okay, so kernel of Dirac operator. So suppose that we have a smooth section of the spinor bundle such that it is in the kernel. So DSMU is 0. So of course, okay, here we need to use the fact that Dirac operator is self-adjoint. Square is also 0. Okay, and by the original formula, we see that first the Laplacian and sectional curvature is 0. Okay, and of course, equivalently, and this part, since the scalar curvature, its lower bound is K0, so it's less or equal to the absolute value of K0 with U. And okay, so from this step, and we should run a Moser iteration procedure. So you can see from the roughly the left part is it contains higher regularity, and is controlled by only U, so it's lower degree regularity, and we iterate this procedure to control the higher regularity of U. Using a Moses iteration, we can finally the control every the L infinity norm of U, and finally uh, compute the this dimension of the kernel. Okay, and in the Moser iteration, it's because of the Poincare inequality. Poincare inequality that the isoperimetric constant comes into place. So the gradient, the L2 norm of the gradient is greater or equal to constant C with the isoperimetric constant, and the F L alpha norm. Okay, we shall use this inequality where alpha is given by 2m over n minus 2. Okay, so using this inequality, we can iterate the above inequality to finally get the L infinity estimate. And in this procedure, you cannot avoid the isoperimetric constant, this isoperimetric constant. Okay, and okay, this is the first question. So we partly answer the first question. Then go back. So if the infimum of scalar curvature is less than 0, so we can still control the hat genus, but with an extra term as parametric constant. So and let's go to the second question. How about the lower degree component of a hat genus? So can we still control it? Okay, the short answer is we can control it, but with a little bit more effort, this a hat genus. Let's give a new interpretation of this a hat genus. So it is actually the top part of the a hat class. The integration of this class is topologically we can write it as the cap product with this. This is the fundamental class, fundamental homology class of M. Okay, so this is this fundamental homology. It is in the top homology of M, and this is top homology HM. So the cut product is a number. Oh, but now we consider the lower degree component of A hat genus. In general, it's I. It's a degree I component. We shall actually control this term instead. So this is in HI homology product with HM top degree homology. The final result is also a homology in HM minus I. Okay, so we shall control this. So first control homology. In what sense? Control, we put a norm on it. So which norm? So the norm is actually the Gromov simplicial norm. Gromov simplicial norm. Its name is norm, but it's actually a semi-norm. So for any, let's denote R for any homology class, it's Gromov's simplicial norm. Let me simplicial the semi-norm. So for a homology class, so you can from basic topology, algebraic topology, you can write it as the sum of AI's coefficient with some simplicials, right? Let's denote as subscript I to denote the i's a triangle, a simplicial, higher dimensional triangle. So we can use some triangle to represent this homology class. And you have many ways to represent. A simplicial norm is it's the infimum of this representation. We take all the representations. This is this in place. So from this definition, roughly, you simplicial norm measures it's the infimum number of simplicials you need to represent this this homology class. Okay, and let's go back. So we shall control the simplicial norm of this homology class. It also depends on scalar curvature lower bound and volume and some isoperimetric constant. So the first question is that how to represent this homology class. We should write it into explicitly into a sum of some triangles, higher dimensional triangles, and compute the supremum of its norm. And then we find an upper bound, right? here we need a higher version of index theorem. By Cohn and Markovich. And actually, we need a quantitative version of their theorem. We need to modify a little bit. The theorem states as follows. Um, we have there exists some functions. Let me put a parameter epsilon. Okay, I'll explain. Then function, a rapid decay function, such that the Fourier transform of this function has compact support. Actually, we can with this subscript epsilon, we can let it the support be in minus epsilon and epsilon. Okay. Then this homology class it can be written as a formal sum for any x0, xi. I shall explain this with this is it's like a cycle. So you have such a function, and you can do functional calculus for the Dirac operator, and this operator is a kernel operator. So you can take the kernel x0, x1, and take from x0, 1, 0, 1, 1, 2, 2, 3, and till the end x0 and xi, and go back to x0. So this is the summation. This is just the coefficient. Okay, so this is, I should take trace times this x0, xi, where for each point, okay, set of points, x0 to xi, and this is in m power I plus 1, we choose a authentic simplicial with vertex x0, x1, x2, x3, for example. So for any set of points, we construct an authentic simplicial of with vertices, those points, and take the summation for all these points. This is a representation of the this is the Poincare dual of the a component of A hat class. And actually xi, so take the sum. This sum is an infinite sum because every x0, xi is on the manifold. We have, so this is just a formal sum. Actually, we need to take an integration over the this manifold instead. Okay, and so with this representation, let's recall the Gromov simplicial norm. It is the sum of the coefficients, and here it's we represent this homology class by an integration. So we shall also replace the sum of coefficients with so AI with integration of product. Its Gromov simplicial norm is less or equal to take the integration and take the absolute value of this very long expression. Move it here. Okay. In other words, here we translate the L1 series of a series or the L1 norm of a series to the L1 norm of a function from discrete to continuous. And okay, and one more thing is this epsilon. The port is in epsilon. It means that we want simplicials not too big, because okay, if the epsilon is okay, it's like the pixel of a video. Epsilon is very small, you can imagine. Epsilon very small, like a video with 1080p, very clear. But if epsilon is very big, then like 360p, the video is not so good. So here is a parameter. So we use we construct the homology of this manifold. Just use simplicial with diameter approximately epsilon. And when epsilon is very small, you can imagine you recover the homological information, but we don't want this infinitesimal. We want a quantity. So let's denote Rm the homological, define homological radius such that it is the supremum of epsilon, such that you use simplicials with diameter epsilon, and you fully recover the homology of this manifold. So you cannot take epsilon to be too small. So sorry, you cannot take it too big. So seems that here an extra parameter comes into play, this homological radius. But let's put another assumption. This is the final result. Okay, 1 minute. Okay. If M is aspherical, which means the universal covering of this manifold is contractible, then the homological radius is infinity. And no matter how big this epsilon, you use the triangle, how big it is, you use to detect the topological information of this manifold, you can fully recover the homology. So because it's infinity, so we can remove this parameter. This parameter goes away, and we can control the simplicial of the A hat of the dual of A hat genus, it is given by also some Cm is 0 with I plus 1 plus 1. Okay, so this explains why there we only still have these two parameters K0 and isoperimetric constant, no extra parameter because it is infinity. Okay, I think I shall stop here. Thank you very much.
Thanks, Qiaochu, for very inspiring talk. And any questions from the audience? Sorry, my background is a bit noisy, so please bear with me. If not, maybe I have a question I should ask. So yeah, when I listen to the first part, so when you control this A hat genus, or you control this kernel of Dirac operator, it reminds me of like an early classical results of Peter Lee. So
Yes.
Peter Lee had a result that's like you can bound the dimension of some finite vector field in any cross section of a vector bundle by the ratio of the L infinity norm. So L infinity
Yes.
norm over the L2 norm by so the maximum value of that. You can always bound the dimensional vector field by that quantity. So that boils down to that boils down to Moser iteration kind of thing. But usually that ratio is like a dimensional constant times that ratio. But here you have a +1. For example, there's an example of this strategy in Peterson's book, which is to control the first Betti number or the kernel of the Hodge Laplacian. In that case, in that case, you get like the first Betti number or the kernel dimension of the kernel of the Hodge Laplacian is bounded by n times something coming from the Moser iteration, and it's just like there's no something like +1, and
Yeah.
when you let the Ricci curvature converges to 0 and the first Betti number converges to a sharp bound, and it seems that in your case if there was no +1, when you let the scalar curvature goes to 0, you should also have 0, which is the perfect bound, but you have this +1, then you cannot get that sharp bound. So is this +1 something from the Moser iteration process, or it's a different
Yes.
method?
Yes. So first of all, we cannot remove this +1. So if we just remove it, this is incorrect because we have examples with K0 be 0, but the E hat genus is not 0. So first we cannot remove this +1, and secondly, the +1 term actually from also from Poincare this inequality is from this term. Here we have a volume of minus of a negative degree. So yeah, we run the Moser iteration procedure, and finally you take the integration over the manifold, so which cross out with this volume term, and you get an extra constant +1.
Okay. But when K0 is 0, is this bound sharp or?
Uh, when sorry, I didn't get it. So you want so where's sorry. So you want to say that this is the can we find optimal constant or something?
Oh, sorry, I'm just, making an analogy of the other result that I was more familiar
Oh,
with,
okay.
the first Beatty number bound. Like,
Oh,
when you have a ridge lower bound, you can do sort of a similar argument to find a bound on the first Beatty number. And in that case,
yes.
if the ridge lower bound goes to zero, the first
Uh-huh.
Beatty number bound goes to a sharp bound.
Oh, so
Like
but
that was
here,
the case there, and I'm not sure
uh,
if there's anything
oh,
similar here.
so here no, we
Oh, okay,
cannot.
okay.
So far, we cannot get an optimal constant.
I see, I see, I see. Okay, thank you.
Okay. Thank you. Thank you.
All right, any other questions? Okay, stop recording.